Today we are going to do 267A, which is 25 to 67 odd. So if you look at problem 25, it says, find all the real zeros and state their multiplicity of each polynomial function. Now, you should be really good at finding roots of quadratics. It's a little bit harder for x to the thirds and fourths and higher. You could graph them and find them, but the more difficult problems in this first set are already factored. So if you look at 26, 26 has two distinct roots. What are they? So this factor produces the root x equals -2, and this factor produces the root x equals 1. And you also need to state their multiplicity, meaning how many times does that particular root show up. So you probably want to do it this way. X equals -2 with a multiplicity of, how many times does that root show up? Well, it's raised to the third power, so it would be multiplicity 3. The next one would be x equals 1 with a multiplicity of 2. Okay, look at 28. How many unique roots does this problem have? 3. Each factor with an x in it represents a distinct root. So this one is x equals -1 with a multiplicity of 4. This one is x equals 6 with a multiplicity of 1. And what's the root there? 0 with a multiplicity of 3. So this 5 here has no bearing on the roots. In fact, you can multiply a polynomial by any, it's called a scalar. It scales the height. You can multiply a polynomial by a scalar and it won't change the roots. It'll change the graph, but not the roots. Okay, take a look at 30. Nope, 30 is the same. Look at 32. How are we going to find the roots of this? So, can I pull anything out to make it a little bit easier? Pull out an x squared, and I get 2x squared plus 5x minus 3. And automatically, I know one of the roots is 0 with a multiplicity of 2. Remind me again what multiplicity 2 looks like on a graph. It bounces off the axis. What does a multiplicity of 1 look like? Straight through. What does a multiplicity of 3 look like? It has an inflection point or a saddle at that. And then multiplicity 4 looks just like multiplicity 2. And multiplicity 5 looks like 3, except it's just a little skinnier. Okay. We need to factor that. Or you could use the quadratic formula. It's up to you. This one has a leading coefficient, so I recommend using the box. We put in 2x squared, and we put in -3. What's the next step? We have to multiply these together because there's a leading coefficient. So -6x squared. Are there factors of -6 that add to be +5? 6x and -1x. So the top row shares a 2x, and then 2x times x, 2x times 3, x times -1. Set that equal to 0. X equals -3, multiplicity 1. And this one, set that equal to 0. We add 1 and divide by 2. So x equals 1/2, also with a multiplicity of 1. Does that make sense? Okay. How would you do 34? So take out 1.2x to the 4th, and we're left with x squared minus, wait, does 1.2 go into 4.6? So 2.4, 3.6, that actually doesn't work. So we end up with 1.2 x squared minus 4.6. This one's easy. 0 multiplicity 4. How do I solve that? Just set it equal to 0. So I'm going to add 4.6. 1.2 x squared equals 4.6. Divide by 1.2. Once I divide it, what's the next step? Square root. And don't forget, you have to have a plus or minus, because you square rooted an x squared. Okay, the next set is just backwards. Find a polynomial, and it says there are many. There are actually an infinite number of correct answers, but we'll all get the same correct answers because we won't use scalars. So for 38, so find a polynomial of minimum degree that has the given roots. So it says don't put in any extra roots, because this one has 3 roots. But technically, we could build a polynomial that has lots more roots and still satisfy the problem. So don't include any extra roots, and I would not include any scalar multiplication. So what would this polynomial look like? Okay. How about if you look at 46? So it has 2 roots with specified multiplicities. So this is the root, so the factor would be x plus 4. And how do I count for multiplicity 2? Square it. And then this one would be x minus 5 to the 3rd. Okay. If you did 44, you can actually make 44 pretty easy. Those are conjugates. And whenever you have conjugates, you could just say x plus or minus 1, well, that won't work. I did it backwards, sorry. X minus 1 plus or minus root 3. And that will, I would accept that answer. If you're doing conjugates, you can just combine those two into a plus or minus. Okay, does that take you to the end? No, that gets you to 50. Okay, 51. For each polynomial function given, A, list each real 0 and its multiplicity. Determine whether the graph touches or crosses at each x-intercept. Find the y-intercept and a few points on the graph. For 51 through 67, just find the roots. Don't worry about that other stuff. Okay. So 51 to 67, all you need to do are find the roots. And there are a couple of them that are trinomials. So take a look at they are quadrinomials. So if you look at 63, you could graph that to find the roots, but you can also factor by grouping. So we can stick this number in the box and stick this number in the box, and we get x to the third, and 4. And then we check if I stick those other two numbers in the box, do they add to be the product of those? So x to the third times 4 is 4x to the third. If I put in negative x squared and negative 4x, if I times those two together, do they equal this? Yeah, and that doesn't happen very often, but it will happen today. So this one happens to work. I can pull out an x, and then this will be x squared minus 4, and this will be negative 1. So my factors are x minus 1, and then does that factor any further? It's a difference of perfect squares. X minus 2 and x plus 2. Or you can find the roots by setting it equal to 0. And you add 4 and you take the square root. Okay, so if you have 4 terms, you can factor it using the box. Just stick them all in the box and verify, is this one times this one equal to that one times that one? And if it is, then you can just factor it this way. One of them will be x squared, and one of them won't. And the x squared one will factor further. Okay? All right. Good luck.